Hello everyone and welcome back to my YouTube channel. Today we will understand second order kinetics for class plus 2. So what is second order reaction? A reaction is said to be second order reaction if rate of reaction is dependent on two concentration term of one reactant or one concentration term of two reactants. Let's understand it. For example, I have reaction A converts into products. So for this we can say R equal to K A raised to power 2. 2 represents the second order reaction. For example, we have reaction like this, A plus B to give products. Now we have two reactants here. So rate will be K A raised to power 1 B raised to power 1, and the sum of exponential power is called order of a reaction. So order here is again 1 plus 1 equal to 2. So second order reactions like these, either dependent on two concentration term of one reactant or either dependent on one concentration term of two reactants. Let's find out the integrated rate equation for a second order reaction. For example, we have reaction A converts into products. At time t equal to 0 second, concentration is A naught, product 0. After time t seconds, concentration is A, and how much product is formed? A naught minus A. Clear? Rate equation is R equal to K A raised to power 2. This rate can be written as minus dA by dt, change in concentration by time, that is a rate of a reaction, equal to K A square. This can be rewritten as dA by A equal to dA by A square equal to minus K dt. If we integrate it with respect to concentration A naught and AT and time 0 to t, integration of dx by x is minus 1 by x. So dA by A square integration here is minus 1 by A equal to minus kt plus c. This is the first equation. C is the integrated rate constant. To find this, we can use time 0 second. So at t equal to 0 second, concentration A is equal to A naught. We can put the value time 0. So equation will be minus 1 by A naught equal to C. This is a second equation. We can put value second in a first. So equation will be minus 1 by A equal to minus kt. Value of C is minus 1 by A naught, minus 1 by A naught. So we can rearrange it, kt equal to 1 by A minus 1 by A naught. This is a integrated rate equation for a second order reaction. We can find out the time t equal to 1 by K, 1 by A minus 1 by A naught. A is the final concentration. We can use it as a AT, concentration at t time, A naught concentration at 0 time. Easy. Next is T half. We have the equation kt equal to 1 by A minus 1 by A naught. At T half, final concentration will be half of initial, AT equal to A naught by 2. We can put the value. So T half equal to 1 by K 1 by A naught by 2 minus 1 by A naught. Solve it simply. T half equal to 1 by A naught. Easy. T half equal to 1 by A naught. Okay, so we can see K is the constant. T half is inversely proportional to A naught, initial concentration. If initial concentration of reactant increase, T half lifetime will decrease. Easy. We can find out the unit of K also. K equal to 1 by A naught into T half. A naught is the initial concentration of reactant. So unit will be 1 by mole per liter second. Unit will be mole inverse liter per second. This is the unit of rate constant for a second order reactions. Easy. Let's do graphical portion also. We have the equation Kt equal to 1 by At minus 1 by A naught. It can be rearranged Kt plus 1 by A naught equal to 1 by At. Simple straight line graph. This is y, this is c, this is slope m, and this is x. So y equal to mx plus c with the positive intercept. So graph will be on y axis we have 1 by At, on x axis we have a t and positive intercept. So this intercept is 1 by A. Slope will be m equal to k. This is the first graph of second order kinetics for 1 by At versus Ta, and we get the slope of k, rate constant. Clear? Second graph we can plot for a T half versus concentration of initial concentration of reactant. T half we obtain 1 by A naught by k. So if we simply plot it, 1 by A naught versus T half. 1 by A naught versus T half. So graph will be straight line, slope will be k. And even we can plot a inversely proportional graph also. A naught versus T half. We can see this is inversely proportional, so graph will be like this. Easy. So this is complete second order kinetics. Let's compare first order, second order, and even a zero order reaction. This is zero order, first order, and second order. For zero order, we have equation Kt equal to A naught minus At. For first order, we have equation Kt equal to 2.303 log A naught by A. And for second order, we have obtained today Kt equal to 1 by At minus 1 by A naught. We can use At also here. This is a integrated rate equation for zero order, first order, and second order. We have obtained T half. T half for first order is, zero order is A naught by 2k. For first order, we have T half 0.693 by k, and for second order, we have T half equal to 1 by A naught k. Here T half is directly proportional to A naught. Here T half is independent of initial concentration of reactant, and here T half is inversely proportional to initial concentration of a reactant. Unit of K we have for zero order mole per liter per second. For first order, second inverse, and for second order we have a mole inverse liter second inverse. This is the summary of zero, first and second order reactions. That's it. Stay at home, keep learning. In next lecture we will understand Arrhenius equation. And do a favor, if you still didn't subscribe my channel, subscribe it. Thank you.